This is the tutorial for the second part of the Scale Model Lab. It is designed to help guide you in what you need to do to complete this lab. In the second half of the Scale Models Lab, we'll be continuing to look at the universe on three different size scales: the solar system scale, the stellar scale, and the galactic scale. We're going to do two different activities in this lab. First, we'll learn how to plot the data on a logarithmic or powers of 10 graph. Second, we'll be doing an exploration experiment where you get to decide what question you want to explore and how you're going to go about studying it. Since this is the second part of the lab, I'm going to assume that you've already finished doing part 1. If you haven't done that lab yet, you should complete that one first. Also note that this lab is based on ideas from two of the online lectures, O1A Introduction and O1B Math. Make sure you've gone through those lectures so that you've got a full understanding of what we're doing here. The scale models we made in part 1 of this lab let us see the relationships between the sizes and distances of objects in space. Another way we can see these relationships is to plot the information on a graph. By making a graph that plots sizes versus distances, we can compare the sizes and distances of different objects to each other. However, before we can do this, we need to make sure that all of the sizes are in the same units. Similarly, we need to make sure that all of the distances are in the same units. We won't know where to plot things if we have some objects with distances in AU and others with distances in thousands of light years. So we're going to have to make sure that all of the distances are given in light years and all of the diameters are given in kilometers. We're also going to need some additional data besides what was given in the first lab. That lab has data tables for the solar system and galactic scales, but it only gives the distance to the nearest star. If we want to include the stellar scale on our graph, we're going to have to add that in as well. Table 1 in this lab lists the distances and diameters for a set of bright stars near our Sun. It also gives the diameters for the planets in kilometers, since that was already given in the first lab. For the other distances and diameters, we'll have to convert the units. Table 1 also has columns for the powers of 10 distances and diameters. We'll leave those blank for now and return to them later. We need to convert three sets of units: the distances to the solar system objects, the distances to the galaxies, and the diameters of the galaxies. We'll go through how we do each of these. The solar system distances are all given in AU. To convert these into light years, we'll use the fact that 1 light year is 63,000 AU. The conversion formula for turning distances in AU into light years looks like this: the distance in AU multiplied by 1 light year and divided by 63,000 AU gives the distance in light years. Make sure you review the unit conversions part of the math lecture as you work on this section. So for example, the planet Mercury is 0.387 AU from the Sun. If we put 0.387 AU times 1 light year and divided by 63,000 AU, we get an answer of 0.0000614 light years. That's effectively just a couple of light minutes instead. Notice that this is a very small number. Remember that AUs are much smaller than light years, so even a planet that is tens of AUs away from the Sun will still be much less than 1 light year away. Use this approach to fill in the rest of the solar system distances on Table 1. The distances we listed in the first part of the lab for the galactic scale were all in kilolight years, which means thousands of light years. To convert the distances into light years, all we need to do is multiply them by 1,000. So the Large Magellanic Cloud, which is 160 kilolight years away, is 160,000 light years away from us. The diameters are also given in kilolight years. To convert these diameters, we first multiply by 1,000 to turn this into light years. Then we use the fact that a light year is roughly 10 trillion kilometers, or 1 times 10 to the 13 kilometers. So the diameter in kilometers is the diameter in light years times 1 times 10 to the 13 kilometers and divided by 1 light year. For example, the Large Magellanic Cloud has a diameter of 29.7 kilolight years. This is the same as 29,700 light years. If we put that into the conversion formula, we get 2.97 times 10 to the 17 kilometers. Remember to be careful with the exponents when you're doing these calculations. Review the part of the math lecture that describes how to enter exponents into a calculator as you do this part. Also notice that you're getting very large numbers for the diameters. This makes sense since a kilometer is a very human scale measurement. It's less than a mile. While galaxies are big enough that it takes light thousands of years to get across them. Do these calculations to fill in the distances and diameters for the rest of the galaxies in Table 1. Also write down a few examples of how you did each of these calculations so that you can turn them in with your lab. One thing you should notice about the data in this table is that the values cover huge ranges. The smallest distances are a tiny fraction of a light year, while the largest ones are hundreds of thousands of light years. Similarly, the diameters range from a few thousand kilometers to more than 10 to the 18 kilometers. If we tried to plot an ordinary graph with data like this, we would only be able to see the very largest diameters and distances. Everything else would be squeezed down to a point at the origin. However, there is another way to plot data that covers a wide range of scales like this. There are several names for this type of graph, including logarithmic, exponential, and powers of 10. We're going to use the term powers of 10 here. To plot a powers of 10 graph, we need to figure out what exponent we would use if we were writing the numbers in exponential form, and just use the exponent part of the number for our graph. For example, if you have a number like 25, then the way we would write that in exponential form is 2.5 times 10 to the 1. It's 10 to the 1 because the decimal has moved one place from 25 to 2.5. So the power of 10 here is 10 to the 1. If the number is 275, then that would be 2.75 times 10 to the 2. Because the decimal moves two places to get from 275 to 2.75, the power of 10 would be 10 to the 2. Notice that we're losing precision here. For example, 800 equals 8 times 10 to the 2, which also has a power of 10 to the 2. When we're focusing on the powers of 10, it's okay that different numbers come out to the same value. Remember as well that if the number is less than 1, the exponent will be negative. Earlier, we saw that Mercury is 0.0000614 light years away from the Sun. In this case, you would move the decimal 6 places so that we could write this as 6.14 times 10 to the minus 6 light years. In this case, the power of 10 is 10 to the minus 6. Go ahead and fill in the powers of 10 columns for all of the objects in Table 1. Some of the numbers in the table may already be written in exponential form. In those cases, you can go ahead and move the exponent over to the powers of 10 column. Now we want to make a graph that shows all of the objects in Table 1. There's graph paper included with the lab, or you can make your own graph using your own paper. The key to making a powers of 10 or logarithmic graph is that each step on the graph paper represents a new power of 10. So if you start with 10 to the minus 6, then the next step will be 10 to the minus 5, then 10 to the minus 4, etc., through 10 to the 0, 10 to the 1, and so on. You should do this for both the diameters and distances. Plot the diameters on the vertical axis and the distances on the horizontal axis. Make sure you label these axes and give the units, kilometers for diameter and light years for distance. One example of what plotting looks like would be the star Alpha Centauri. We know from the table that its diameter is 1.8 times 10 to the 6th kilometers. So the powers of 10 here is 10 to the 6th. Its distance is 4 light years, which is about 10 to the 0 light years. Start at the 10 to the 0 light years mark on the horizontal axis and plot upwards to the 10 to the 6th kilometer line and put Alpha Centauri there. Plot all of the objects in Table 1 on the graph. Make sure you choose your axes so that everything fits, and try to use as much of the graph as possible. If you have room, try to label each object you plot. Also, you should give different symbols for each type of object: solar system, star, and galaxy. Also note that in some cases, you may find that more than one object is plotted at the same point. That's not a problem. Just put both names by that point. You should see the three major scales we've discussed show up clearly on the graph. This will give you a better sense of how the solar system, stellar, and galactic scales compare to each other. Once you've finished your graph, also notice that there is a discussion question at the end of this section. Think about where else you may have seen graphs like this. They sometimes appear in news reports or other places where people need to plot numbers with very different sizes. Go ahead and answer this question based on the powers of 10 graphs you've seen. The other part of this lab is the exploration experiment. This is a chance for you to apply the ideas we've been working on to your own experiment. You'll notice that there aren't a lot of instructions here. You're going to have to decide yourself how best to approach this. We've given some suggestions on experiments you could do. One of these involves making your own scale models of objects like the Earth-Moon system or the Milky Way galaxy. Or if you've been assigned a mystery solar system or your own constellation, you could make a model of that. You'll have to look up the data and then decide how much you need to shrink all of the sizes to make your model manageable. Note that you don't have to do a powers of 10 graph for this unless you think it will help you understand what you're working on. Another option is to look at some other class of objects in space, such as globular clusters or planetary nebulae, and decide which size scale they best belong in. Are they on the solar system scale, the stellar scale, the galactic scale, or do they fit somewhere between the scales we've defined? You'll want to compare to the graph we've made to see how they fit in. You could also look at the brightnesses of the stars in the table or in your constellation, if you've been assigned one, and see if those brightnesses are related to the distances the stars are from us. You're also welcome to come up with your own questions related to distances and sizes of objects in the universe. You should check with your instructor to make sure your question is a reasonable one to tackle with the tools you have available. Remember that in the exploration experiment, you need to work with the data yourself to answer the question. So it's fine to look online to find sizes, distances, or brightnesses you need. But if you're just looking up the answer online, then you're not really doing an experiment. Also notice that the exploration experiment is a big part of the points for this lab. So plan on spending some time on this part. In addition to doing the experiment, you'll need to explain what you did in detail. Give any data you used and any calculations you did, and make sure you describe any conclusions you came to from your experiment. So have fun, and ask your instructor if you have any questions on this or any other part of the lab.